Before proceeding with this video, please do make sure that you watch the preceding video that got into why are we studying limits. What are they going to help us do in calculus? I do think it will be important to have that perspective as we move forward with our studies in limits. But this video will get into how do we deal with limits, and specifically, how do we deal with them graphically in this video. Later on, we'll get into numerically and algebraically studying limits, but we're going to focus on the graphical aspect of them in this video. And this will be the function that we use as an example. Now, to be clear, this is all one function. Sometimes students will mistakenly look at that and think that I'm intending to have one function here, and then a separate function here, and then a third, and then a fourth function here. No, this is all one function. Notice that this function happens to have several discontinuities, but notice that it doesn't violate the vertical line test, and my intent is for it to all be represented by function f of x. And from the last video, and possibly from our previous exposure to limits in pre-calculus, you understand that limits are about approaching a certain value, and we're going to be very clear on that distinction between how limits tackle what happens as x approaches a certain value versus what happens at that value. Those are two different things that you'll need to be clear on by the end of this video. So in this graphical example, in this graphical representation of f of x, let's start by taking a look at what happens in the vicinity of x equals 6. In my GeoGebra representation here, I'll zoom in a little bit on or around the area of x equals 6, around the region of x equals 6. And first thing to notice is that there is a hole at x equals 6 on this function. There is a removable discontinuity, but let's focus on what happens with the approach as x approaches 6. Right now, the point that I've highlighted there in pink there has an x value of 5 and a y value of 2.732. And as I approach x equaling 6 from the left, and that's the vocabulary we'll use, is I'm approaching from the left. That's when the x values are a little bit less than 6, to the left of 6 on the number line. Notice as I'm approaching x equals 6 from the left, the y value is decreasing. The y value right now is 2.246. Now the y value is 2.179. And clearly the y value appears to be approaching 2 as x approaches 6 from the left. Now, key thing to notice is that once I get to x equals 6, once I arrive at 6, I don't get the satisfaction of seeing the y value equaling 2. But that doesn't matter. We will still say that as x approaches 6 from the left, the y value is approaching 2. Notice that the same happens on the right. If I go right of 6, if x is like 7, for example, here, as I approach from the right, the x value is always a little bit higher than 6, but the y value is a little bit lower than 2. But once again, I see that as x approaches 6 from the right, the y value is approaching 2, this time from underneath, a little bit less than 2. However, once again, I'm never given the satisfaction of actually seeing y equal 2. So, when we ask the question, what happens at x equals 6, we will say f of 6 is undefined. There was a hole there. And as a very picky point, instead of saying equals undefined, I'll say is undefined. Now, as far as what happened as we approached x values of 6, that's where we'll use the limit notation. And hopefully you remember some of that from our previous exposure to limits in pre-calculus. When we were approaching from the left, when we're approaching from x values that were slightly less than 6, that's where we will put a little minus sign up here. Don't confuse that with an exponent. It doesn't mean 6 to the negative power. It just means 6 from the left. And we said that as x approaches 6 from the left, the y value was approaching 2. Important thing to notice here is we're not claiming that the y value ever reached 2. We just are saying that 2 is the value that y was getting closer and closer to. Now, how about from the right? We will similarly say that in this case, in the case of x equals, or x approaching 6, when x approached from the right, we also found that the y value approached 2. Because the limit from the left and the limit from the right both gave us the same value in this case, both gave us the same value of 2, we may also just say that x approaches 6 without specifying a direction from left to right. If we just say x approaches 6 without a little minus or plus superscripted there, we'll say that the limit of f of x is 2. And again, we will do that because the left value, the approaching from the left value and the approaching from the right value were the same number, so that same number just goes here. Now, hopefully you're already wondering, hopefully you're already anticipating, under what situation might the approaching from the left and approaching from the right and overall limit differ. Well, let's see such a case. Let's now turn our attention to the vicinity of x equals 4. Back in GeoGebra, this time if I start at an x value of 3 and start approaching x equals 4 from the left, I see that x value is, well, 3.5, 3.6, 3.7. It's approaching 4 from the left. The y value is 2.5, 2.4, 2.3, 2.2, 2.1. Clearly the y value is approaching 2 from the left. Now, once I actually reach 4, the y value is something else, but that doesn't matter when we're talking about the limit. The limit is all about the approach. So, one more time, from the left, the y value is approaching 2. So let me go ahead and go back to this screen and fill in when x is approaching 4 from the left. We said the y value was approaching 2. That's what this limit notation means. Now back to GeoGebra. We also said that once I reached x value of 4, our y value in this case is not a hole. There is a point filled in there, and we see that when x equals 4, y equals 4. We're not talking about limits now. We're talking about what happens at x equals 4. So we can fill in at x equals 4, the y value is also 4. Notice the absence of any limit notation there. All right, back to GeoGebra. I'm kind of jumping around a bit here. Let's now approach x equals 4 from the right. So I started x equals 5, 4.9, 4.8, 4.7, 4.6. X is approaching 4 from the right. And I see the y value is approaching 4. Now, even though it reaches 4, that's really not the question we're asking when we're talking about limits. I'm more interested in the fact that it is just clearly approaching 4. So, back to this screen. As x approaches 4 from the right, the y value is also approaching 4. Consider what would change. What if instead of having a filled-in point at x equals 4, what if we had had a little empty at the end of that branch of the curve there? What would change on the screen? Well, the limits would not change at all. This 2 and this 4 would not change at all. However, instead of having f of 4 equals 4, we would now have to say undefined at x equals 4. Okay, I hope this is making sense. There is a lot of nuance in this topic, so absolutely please attend office hours if any of this is not making complete sense. But now let's discuss what about the fact that the limit approaching 4 from the left and approaching 4 from the right were not the same number. Because the limits from the left and right don't equal each other, in that case, this overall limit here, we will put does not exist, and it is considered an acceptable acronym to just put DNE for does not exist. Now, if you put undefined there, not the biggest deal in the world, but typically we will use undefined when we're talking about the what's happening at. I would use undefined up here at a certain x value. But when we're talking about the limit, we usually just conventionally use the notation DNE for does not exist. And again, nitpicky detail, I would prefer to avoid using an equal sign there. Not the biggest deal in the world. Okay, let's now turn our attention to what's going on in the vicinity of x equals 2. Starting at an x value of 1 to the left of 2, as I start approaching an x value of 2, I see that the y value, currently at 0.586, now negative 0.078, now negative 1.165, As I get closer to 2, an x value of 2 from the left, I can tell that the y value is really starting to plummet downward. And it even goes off the screen here. And we can, if we're confident that there's an asymptote there, we know that that means that the y value is going to just plummet indefinitely towards negative infinity. So back here on this screen, this is one of those little nuances. There is an argument to be made. There are some, by the strictest definition of limits, in a textbook, you'll often find that a limit is supposed to be a real number. You can only put a real number over here. That's kind of the most strictest interpretation of the rules. But I'm going to not go that route. There is a kind of common convention to say that when a y value is approaching either positive or negative infinity, there's a common convention to say, all right, let's just go ahead and put the y value is approaching negative infinity, therefore the limit equals negative infinity. Conceptually, this is a little problematic. It seems a little wrong to say or imply that anything equals negative infinity, but we're going to allow ourselves that because it is a common convention. But don't be surprised if in a textbook someday you see a book claiming that in this case the limit should be does not exist. All right, back in GeoGebra, as I approach x equals 2 from the right, the y value is clearly getting closer and closer to 4. May not actually get the satisfaction of seeing it say 4, but we know that the y value is approaching 4 from the right. So x approaches 2 from the right. I'll put a 4 for that limit. Once again, we see that these two limits, the left-handed limit and the right-handed limit, do not agree. So we know what that means, right? Does not exist for the overall limit. Now, what's happening at x equals 2? Back on the GeoGebra screen, we see that that's where we had a hole at the end of this branch of the curve. There is no point on this function at x equals 2, so we will say undefined for f of 2. I repeat, sometimes students get these two mixed up, undefined and D and E. It's not the biggest crime in the world, but undefined is what we use at the value. D and E is what we use for limits. Now, what would change on this screen if I added a point to that function? Let's say I put the point right here and said that was included in our function f of x. What would change there? Well, once again, notice that nothing changed about the approach, so nothing will change with these limits here. However, by adding that point, I do have f of 2 equals 7 if that point is included in the f of x. Okay, let's do one more, and I'm not going to pretend that this video is going to answer every single question you will come up with regarding approaching limits graphically, but hopefully it gets you 90% of the way there, and through your own ingenuity or through attending office hours or using other resources, you can kind of fill in the gaps that I'm not covering here. Okay, one more. Let's talk about what happens as x approaches infinity. What about when x goes past these values and just continues to the right indefinitely? X approaches infinity. Back in GeoGebra, let's rescale the axes and clearly see, I think you can anticipate what's happening as x gets bigger and bigger and bigger. As x grows and grows and grows in the positive direction, look at what's happening to that y value. Right now it's 1.111. Now it's just a tiny bit over 1. As I keep going to the right, we know how horizontal asymptotes work. It's just going to get what we would say is infinitesimally close to 1, arbitrarily close to 1, as x approaches infinity. So what does that mean back in this screen? First of all, whenever x approaches either positive or negative infinity, I don't think you're really ever going to see in a textbook either of these one-sided limits. When you're dealing with the case of infinity, you really will only ever see this limit in a textbook. But I do want to address those other two just to see if we can agree what makes sense to do in those cases. So, as x approaches infinity, wasn't it clear that the y value is approaching 1? We're not concerned that it will never equal 1. We'll just say the limit is 1. Now, I'm going to claim that one of these two one-sided limits doesn't make any sense at all. It's a bad, invalid question. Would you agree that this one doesn't make sense? X approaches infinity from the right. Doesn't make sense. Infinity is the concept of being larger, farther to the right than any number you could possibly write down on paper. How could you possibly approach infinity from the right? So On an assignment that I give you, I will reserve the right to ask this question, even if textbooks don't ask that question. And if you see it on an assignment or on a test, I'm going to ask you to cross it out and say, that is a bad question. It is an invalid question. That doesn't make sense. That's not the same as does not exist. This is sort of like that got disqualified. X approaches infinity from the left, on the other hand. Not only is that possible, but that's the only way you can approach positive infinity, isn't it? You can only approach positive infinity from numbers that are less than positive infinity. So, once again, the limit is just 1. Automatically in this case, because this limit got disqualified, automatically these two limits are just going to be the same thing. And I repeat, you're really only going to see this limit. You're not going to see the from the left symbol in the textbook. Now, as far as what happens at infinity, I'm going to say that's also a bad question. I know it's tempting to put 1 there, but technically 1 is not in the range of the function, or at least not along this branch. There is a y equals 1 over here, but if we look at this branch, y is not in the range of that branch. This is a bad question because infinity is not a number. When plugging values into the function, you can only plug real numbers into functions. Well, at least at this level of math, until you get into complex numbers and such. But since infinity is not a number, that is another question that I don't think you'll really see in textbooks. But if I ask you that, I want you to say, bad question, disqualified. Okay, I hope all that made sense. Your assignment will look a lot like this example. Again, you may find some little scenarios that come up in the assignment that weren't exactly covered in this video, but I want you to make your best attempt at it, and we'll address issues as they come up moving forward. All right, bye for now.